Good morning, guys, and welcome. Today is Tuesday, March 16th, okay? And we finished chapter 23. We are supposed to do chapter 24, okay? I think we are on track in this class. I'm not sure, okay? So probably if we are just a lesson behind, okay? So that's the most that we should be in terms of schedule and things like that. Let me refresh the screen in here quickly. Okay, so let me get into my notes in here. Oh man, why is it doing that? Okay, good. So let me share with you. So you guys are looking at the screen that says basically one note that has chapter 24 on it. Yes, no, maybe?
Yes.
Yes.
Very good. Okay. We started this class, what, a month ago? Just a little less than a month ago, okay? And we started with chapter 21. Basically, we said that we're going to discover a new force in this class, and this force is the electrostatic force, basically, that if I have a charge, okay, that charge is going to be inside an electric field, and so that this force must be back to chapter 4 or something like that, way back from physics 4a, F equals to ma. Since I know what the force is, I can find now what the acceleration is, okay? The electric field was really the headache that basically we had to struggle through, okay? The idea is the following. If I find the electric field, namely how is the distribution of a charge modify the surrounding its area, basically how it changes it. Now, if I bring charge mix to the mix, namely Q, that charge is going to be under force given by this force in here, which is the electrostatic force, the equivalent of Coulomb's force. So the problem then became of finding E. Chapter 21 dealt with really the brute force of doing that. Just sum the thing. Do an integration, okay? Find E, basically, that way. And we can use that method if everything else fails, basically. This is still a valid method no matter what. If you can do it because of basically our inability to do integrations, that is something else. But theoretically, there is no limit to what we can do with this method, okay? Chapter 22 came up with an idea of symmetries and came up with a theorem equivalent to the first one. As a matter of fact, there is a one-to-one correspondence between the two that basically says the flux of the electric field over any closed surface, how is it flowing? How is it going out, basically? The field lines, how many? That is the flux, really. That is equal to the charge enclosed divided by the constant, namely epsilon naught, okay? So that provided a means for us, a trick, if you wish. When there is symmetry, that turned out to be a useful way of doing things and finding the electric field. So in the case when there is symmetry, this Gauss's law that basically states that the flux of the electric field over any closed surface, so the circle in here means closed, and in here is any, actually. It doesn't have to be a sphere or anything like that. It can be any surface. As a matter of fact, sometimes sphere is not good, especially, for example, for wires. We ended up using cylindrical surfaces, okay? Is equal to the charge enclosed divided by epsilon naught. This provides itself very, very useful for us when there is symmetry. If there is spherical symmetry, use a sphere. If there is cylindrical, use cylindrical symmetry, use cylinder. As a matter of fact, we use actually at some point what looks like a cube for the case, for example, of an infinite plane. So when there is symmetry, yes, go ahead and use this one. Otherwise, it's going to be as hard as this guy, the brute force, basically trying to find E as the sum of all of the elementary charges, dq, producing an electric field somewhere in space, okay, and summing all over this one. This is actually a triple integral because you're summing through volume of these charges. So there is a distribution of charges in here in space, okay? So this is not it's not what it looks like. It's not a single integral. This usually involves triple integral too. That's why this method is usually, when nothing else succeeds, then you come back to it. And if you cannot do the integrations basically by analytical integration is basically finding a formula for it. What do you do in this case? You get a computer, turn on your coding abilities. If you know C++, go ahead. If you know Python, go ahead and sum through that thing and find the sum and improve your calculations basically based on the finite spacing that you're going to take for your samples, in this case dq, and that's going to give you a good enough result for how much the electric field in some point in space. And from there, you bring a charge, then that charge will be subject to this force, which bring you back to physics 4a to find the acceleration, okay? So that is basically the approach with these two chapters. Chapter 23, though, came up with a clever technique, basically, and discovered that the fact that the electric field derives from the potential, okay? Then instead of solving for this three integrals, because regardless of the geometry, you're going to be dealing with three components, Ex, Ey, Ez in Cartesian coordinates, or radial and the two angles in the polar coordinates, or whatever system that you're using, you have three components for a vector in space. So this is, in general, involves that much calculations, especially when the geometry is not symmetrical and not regular. Then the summations I was talking about in terms of computers would require actually three components. So this one says, you know what? You can do away with just one of them. That's it, okay? The potential, a scalar, a number. Okay, what happened to the mouse? Sometimes the mouse disappears on me. It's in here. So you deal with a scalar, which is just a number, okay? If you find that number, which is not easy also, but it's actually easier in the sense that you're dealing with just one number, okay? This is, again, a volume integration, and this has nothing in it. This is not a vector or hat. You don't have to worry about the angles. You don't have to worry about the orientation or anything like that. Once you sum this number, now you have V, then you take its derivatives. Usually taking a derivative is easier than taking than integrating, okay? So once you take its derivative, you find the electric field, and now you're back in business to where we started from, and you're in here, okay? You guys saw that we never really did this step because it's really just a fake thing, okay? We never really were intending to do this, although sometimes we did. But the intent in here is that we're an inventor of a new kind of a phenomenon in physics. That is basically what this idea is leading to. So this is was a setup, okay? That's all. It's part of a plot, if you wish, okay? It's never really an end by itself. However, it was an end by itself for the following case. Let me tell you what that case is. Remember the parallel plates from chapter 23? When we had a sigma charge in here per unit area, so we assume that there is an area in here, A, of some big plate in here, and there is another plate in here where we borrowed those charges. So this is the same area A. The separation between these two was D, okay? And D is a lot smaller than the area A to justify that the fact that the electric field in here was 0, the electric field in here was 0, and the electric field in between was twice as much as that of an infinite plate, which turned out to be sigma over epsilon naught, end of the story. So in this case, if I bring a positive charge and drop it in here, okay? So the electric field is raining down now. The electric field is pointing down. It's from positive to negative. This is how the electric field is actually pointing. So if I put a negative charge in here, it's going to be subject to an acceleration with the electric field. It's going to point down. As a matter of fact, I can find the acceleration. It's going to be, per Newton's law, it's going to be F over ma, and F is a QE, and E is sigma over epsilon naught. So it's going to be Q sigma over epsilon naught, but don't forget the mass in here, okay? So a proton, which is heavy, will fall down with this acceleration. It's not really that heavy, okay? So this is tremendous acceleration. The mass of the proton, by the way, is 1.67 times 10 to the negative 27 kilograms, and that's super, super light. So as a matter of fact, the acceleration is going to be upstairs. Yes, you're telling me, how about the charge of the electron? It's 1.6 times 10 to the negative 19. It's still 10 to the negative 19 divided by 10 to the negative 27. That's 10 to the power 8. meter per second per second. This is tremendous acceleration. Okay, this is not 10 meters per second per second. This is not G. This is 10 to the power 8 meter per second per second. Okay, provided this number is also actually big too. So this number will make this number even bigger. This number is of the order of 10 to the power 9. So this whole thing is going to be 10 to the power 17. And depending on sigma, which is usually of 10 to the negative 6, so now you're taming it down. So it's going to be 10 to the power 11. It's still tremendous acceleration. Okay? No matter which way you cut it. Okay? However, if you bring an electron in here and you do the same calculation, everything stays the same, except the mass of the electron now is a lot less. The mass of the electron is, what is it? 9.1 times 10 to the power negative 31, okay, which is roughly 10 to the negative 30, which is about 1,000 times lighter than this one, which makes this acceleration 1,000 times higher. But it's going to accelerate upward because it's a negative charge. This charge is negative, actually, okay? So it's going to accelerate upward against the electric field. And basically, at that point, it's going to fall to the upper plate with tremendous acceleration. If this was 10 to the 11, this will be 10 to the power 14 meter per second per second. So if you have G there, ignore G. G is just 10. Okay? It's not going to have any impact whatsoever. So this is basically an analysis, if you wish. Now, if you bring these charges and you give them an initial velocity this way, if this was an electron, I mean a proton, and the proton was accelerated this way, I mean was given an initial velocity this way, this is just a projectile that we could have done. This is just a projectile motion. And we will find where it's going to land on the lower plate. If it was an electron, okay, and you give it the same thing, it's going to have tremendous acceleration though. It's going to land closer, but it's still a projectile nonetheless. So both of them are projectile motions. That is physics 4A. Except the acceleration now is not G, is not this guy, these numbers, which are tremendous numbers, okay? So that is basically how this thing. So the proton will deflect to the lower plate, to the negative plate. The electron will deflect to the upper plate, the positive plate. End of the story. So this, we could have made that argument based on this stuff, okay? And that is basically fine. That is good. So let's see this device now up close. This is chapter 24, by the way, after all. It's not the other chapters. So let's see what this device does for us. So then I'll draw it again. So there's some area somewhere in here that extends in space. It's big space in here, relatively speaking, compared to the distance between them, okay? So this distance is D. What I'm saying in here is this A I drew, it's probably comparatively speaking the same size, but they're actually huge the separation for the formula to work, for the electric field to be 0 outside and to be a finite value raining down from, because at the end in here I have a charge Q, and the charge Q is exactly equal to sigma times A, because sigma is the charge over area, okay? So this is the charge Q that I have actually managed to assemble in here. And this is the charge negative Q that I have to basically assemble on this side. And the Q is the same in magnitude, okay? Because remember the process I described last time is I borrow an electron from here. When I take an electron from here and put it in here, I will have a negative charge in here, and I will leave a positive charge behind, a positive ion behind. So that's basically the picture. And we did this, and at the end, we found an electric field in this region that is sigma over epsilon naught, or if you like to write it in terms of these numbers, it's Q over, what is it? A epsilon naught, okay? In terms of the electric charge. When we calculated the electric potential, where we put V equal to 0 here, and V some value in here. As a matter of fact, V is equal to E times D in this point, okay? V in this point is equal to this electric field, which is sigma over epsilon naught times the distance between sigma over epsilon naught times D. And then you can write this V in terms of Q actually too. You can write it as Q over A epsilon naught times D, okay? So this potential difference between the upper plate and the lower plate is the following. V is equal to Q over A epsilon naught divided by D. This is what I did to this expression. I moved the D in here, which is multiplying the electric field, and it divided it by the denominator. It's the same thing. Do you guys agree that this is identical to this expression?
That makes sense.
Yeah, so it's all we did is just manipulate the numbers, that's all. Let's look at this expression, what's going on in here. This, I can write it as follows. V equal to Q over C. Let me tell you what C is. C, first of all, it's clear from my definition that is going to be A epsilon naught divided by D. The C has to do with the geometry, how big the area is, and how much separation do you have between the two plates, okay? It also has to do with the medium between them. I assume that there is air in here. That's why I put epsilon naught in the formula in here, okay? If there was no air, if there was a different material, I will have probably to get its permeability in there instead of that of the air, okay? So this does not depend on the electric field, for example. It does not depend on the potential, for example. It does not depend on the charge, this C. It's independent of them. So it's a property of this device itself, which I'm gonna call up front right now the capacitance. So this is what I mean by capacitance. So what does the capacitance then mean? Obviously, C is equal to QV. I'm sorry. Q is equal to CV. Okay, I'm sorry, that's a mistake, clearly. So what does it mean in here? Let's say, for example, you have a battery that is worth 10 volt, a battery. You bring a 10 volt battery. And you would want to have, for example, I don't know, let's say, for example, 10 micro coulomb in here, okay? That is what you want to do. How can you do a 10 micro coulomb with 10 volt? Here is the formula for it. Cook your A and D in epsilon naught just enough. So this relationship is working. So your 10 micro coulomb is equal to the C that you're going to cook from this equation times your 10 volts, okay? So how much does C need to be then? Remember, this is 10 times 10 to the negative 6 coulomb, and this is C times 10 volts. So how much do we really have to have C in here to make this equation work? This is coulomb, by the way.
Nano?
No,
Nano's -9.
So is it micro then?
Yeah, micro.
Okay, it's 10 to the negative 6, clearly. Yes? Yes?
Yes, Professor.
Yep.
Whatever unit we're going to put in here, okay? The unit we're going to call it. Yes.
In the examples I was practicing, they wanted you to, well, not you, but like they wanted the people practicing the book to convert it into a unit where it's not 10 to the negative. So like if it was to the -6, it asked us to convert it to just coulombs, and we'd multiply the initial number. So in this case, it would have been,
Micro.
yeah.
Yeah, that's a good practice, okay? We're going to get to that point, okay? You're a step ahead of us. Okay. So we're going to use it's a micro, so that's the unit. So forget about the units for right now. It's a coulomb over volt in here, okay? But we're going to get into the units at some point, okay?
Okay, thank you.
No problem. The point being in here is that I can cook my A and my D if I am forced to use the same epsilon naught in such a way that this number is 10 to the negative 6, basically. That's the bottom line to it, okay? So if I do that, then I will have 10 microcoulombs in here. Let's say, for example, I really don't want 10 microcoulombs. I want more charging. I still have only 10 volt, by the way, okay? I still only have 10 volt battery. I don't have more than 10 volt battery, but I want more charge in here. I want 100 microcoulombs in here. I want to go big, okay? 100, more than 10. So what should I do now? So it's going to be 100 now. Microcoulomb. This must be equal to C times 10 to the power 10 volts. So what's the number in here that needs to be for C now? Is it going to be the same number or is it going to be higher?
It's gonna be higher.
Okay, it's going to be 10 times 10 to the negative 6, basically, or 10 to the negative 5. Whatever unit you choose to put in here, okay? So we're going to fix that problem quickly. The point being in here is, then as an engineer, you come to the geometry, change the area just enough, make it bigger, or make the D smaller, okay? Than the first time. And now you have already a bigger capacitance so that this can handle your 100 microcoulombs for that same 10 volts, okay? So that is the meaning of the capacitance. So it's an engineering issue, really. Now, short of doing this, you can bring another material in here with a higher epsilon naught. Epsilon naught for air and the vacuum is the absolute minimum. It's that the smallest. Then if you have material that has a higher, basically, permittivity, which is any material, basically, especially it has to be an insulator, it cannot be a conductor. If you put a conductor in here, it's going to conduct electricity, and now you're lost your stuff, okay? If it's not conducting, you're going to put it in the middle, and there's going to be another capacitor, which is a problem. So it has to be an insulator. If you put your insulator in here, you put your insulator in here. So there is a block of material in here that has an epsilon relative higher than 1. So in this case, what that means is this positive charge will induce a negative, positive charge will induce a negative charge in here, and the negative charge will induce a positive charge in here, okay? And the distance, as if now, is just this distance and this distance between the two plates. It has already went down, okay? You shrunk the distance this way. If you shrunk this way the distance, then D went down, the capacitance went up. Without doing any geometry stuff, you could just have put another material in there, which is called the dielectric material, okay? So this is, you have options as an engineer on what to do to make this thing happen for the requirement for your applications. If you really need 100 microcoulombs in here, you can manage that, okay? You can manage that by playing with either the geometry or the material between the plates, that's all, okay? So this is what the meaning of the capacitance is. How many coulombs can you put in a certain place? That is basically the bottom line, the problem you're facing as an engineer. And you do that by changing the geometry, okay? And or the material. As a matter of fact, this was not true for this one in here. Marcella, please remind me quickly about the units because we need to come back to them. Or since we're talking about units, let's hit that point in here. Very important. Units. Okay, here is the deal. The unit for the capacitance is clearly the ratio in this case of the unit of the charge, which is a coulomb, divided by the unit for a volt, okay? Remember the unit of the volt is, remember the volt times the charge, which is a coulomb, is a joule. That we saw because the potential energy is a QV. The potential energy is always in joules, the Q is in coulomb, and the V is in volts. So it's clearly the volt now is the ratio of the joule over a coulomb. So that is going to be a coulomb squared divided by a joule. Coulomb squared is, we're going to see that next chapter actually, it's the current times the time, basically. The current is the ratio of charge per unit time, okay? So in this case, the coulomb is going to be an ampere squared, second squared. The joule is a mass times acceleration, that's a force, Newton, times distance. So it's a meter. So it's a kilogram, meter times meter, which is meter squared per second squared. So this unit for the capacitance, this is the capacitance, by the way, is going to be an ampere squared, second to the power 4, divided by a kilogram meter squared. Obviously, we get sick and tired of calling it kilogram. I mean, ampere squared, second to the power 4, kilogram meter squared, and who in the world is going to remember that, okay? If everything is in SI, if the voltage is in volt, the charge is in coulomb, the forces are in Newton, and everybody is happy, then this guy has a unit now called the Farad. Okay, so this is a Farad. Okay, so the unit for the capacitance is the Farad. If everybody, in honor of Mr. Faraday, by the way, and if everything is in SI, provided in SI, okay? Le Système International. That is, provided that you're in that system, you're in good shape. Okay, now, Farad is too big of a capacitance. As a matter of fact, if you look at all of the devices that we have in the laboratory, they are of the order of a microfarad, a nanofarad, or a picofarad. And the lab that we're going to do on Thursday, it's going to be of the order of a picofarad, 10 to the negative 12, as a matter of fact. Where is my device that I had yesterday? Here. This is how the capacitance would look like. This is an old video card, by the way, okay? So I didn't want to remove this part in here, the cooling part of it, because I think it still works. Anyway, this is how the capacitance would look like, okay? So it looks like it's like a cylindrical chamber in there, okay? And if you look at the values, you can read the value in there and see how much it is. It's usually of the order. So in your calculations, it's a good practice, like Marcela had mentioned, to leave the units for whatever they are. We're going to do an example. So if it's on a microcoulomb, the charges, the unit for it is going to be a microfarad, okay? So keep the things, if it's in a nanocoulomb, the charges, keep this guy in a nanofarad, and so on and so forth. Work your numbers, and then the answer at the end, append to it whatever that thing is, okay? Don't forget, though, that the micro is 10 to the negative 6. And the nano is 10 to the negative 12. And the pico is 10 to the negative, 10 to the negative 9, the nano. And this guy is 10 to the negative 12, okay? And the femto is 10 to the negative 15, and so on and so forth, okay? So these are something about the units. Let me go back into the problems that we did. I think problem 41 and problem 61 from the previous chapter, okay? Problem 41, we had two spheres, if you guys remember. Sphere over inner radius A, or RA, I think they call it there, and outer spheres of radius B. And at that point, we found that the potential difference between the upper plate, which was at potential, this was a positive charge Q, or no, I'm sorry, this is a negative charge Q. What am I saying in here? And this was a positive charge Q. That is a problem that we did last time. The electric field in here turned out to be 0. The electric in here field is because it's a conductor is 0, and in here because the charges are 0. The electric field in here is some function of R, okay, which we don't care about it. We found the potential difference in here. The potential in here, we took it to be 0 because at infinity it was 0. The potential in here was that V. So the potential difference, really what matters is not the potential at a given point. What matters is the difference in potential. Same thing is true here, by the way. This is actually the potential difference. E times D was the potential between the difference between the lower plate, which was 0, and the upper plate, which is E times D. So it's always the difference that matters, not the actual potential. When the power company tells you we're giving you 120 volts, what they mean with it is the difference between the two basically ends of the plug, because there are two holes in it. The difference between those two ends is 120 volts. So one of them could be 17 volts. The other one is 137 volts, and you can do the math. If one of them is negative 10, the other one is actually 110, so that the difference is still 120 volts. So what matters really is the difference between the two plates, and not, so this expression that I wrote earlier was not really stating it explicitly, but it was implicit that this is actually the difference in potential and not the potential at a given point. Because the potential is an integral and is defined within a constant. So where we choose a constant, that is really where the 0 is. So where I put this plug from the ammeter is going to be the 0, okay? So where I put the other one is going to be the difference between them, that's it. So what the ammeter is measuring in this case is the difference between the red and the black, in this case, plug, the COM port and the regular port, okay? So the difference in potential, if you guys remember, correct me if it's wrong, was Q over 4 pi epsilon naught times 1 over A minus 1 over B. I think we used RA and RB in this example at last time, okay? So this is no different than the other problem. This looks like V in this geometry is Q over 4 pi epsilon naught divided by 1 over A minus 1 over B. In other words, this is actually still Q over C, where C in this case is equal to 4 pi epsilon naught divided by 1 over A minus 1 over B. This also depends on the geometry. how big the radius of the inner sphere? That is A. How big is the radius of the outer sphere? That is B, basically. In other words, the separation between them, okay, between the two spheres. Okay, that's really the geometry. And epsilon naught is the material in there. So if you're not using epsilon naught and using a different material, in this case, the expression is going to be identical, 4 pi epsilon naught divided by 1 over A minus 1 over B times epsilon R, where epsilon for any material is actually the epsilon R times epsilon naught, where epsilon R has no units. So basically, relatively speaking, how the permittivity of this medium is different than that of vacuum, okay, or the air. That is epsilon R. So that's basically the expression to it. So you can play with the material inside, same thing as before, or you can basically put a change the geometry, and at the end you achieve the same goal with this capacitor. The same thing with the other capacitor from problem 61, I believe, where you had actually two coaxial cables, one inside of the radius A also. So this distance was A, and another one outside. I'm exaggerating the geometry in here. In practice, this is not correct, okay? Geometry is very close from one another. This is B, and again, there was a lambda charge per unit area in this case, where lambda is related to the charge divided by the length of the entire wire. So there is a finite length in here, okay? Although we assumed it's too big to be compared to A, that's all, or B, that's all, okay? But not infinite. There is no such a thing as something infinite. As a matter of fact, if you do these measurements with this geometry, you're going to get a very good answer. You're going to get the infinite wire or the infinite plate will work beautifully for this geometry, okay? So unless you come to the edges where the issues start to become an issue, same thing in here. With this capacitor, we use that, okay, where the edge becomes an issue. For spherical geometry, you get rid of that problem altogether. That's why a lot of technologies have these geometries in them, because they avoid that issue of the edges with spherical excuse me, with spherical geometry. In practice, you can do spherical geometry for capacitors. So you use actually cylindrical geometry. Okay, it's easier. So you get rid of some of the problems, but not all of them. Okay. So in this case, it turns out the potential was equal to lambda over 2 pi epsilon naught ln of the ratio of B over A, okay? Lambda, remember, is Q over L. So this is actually Q over 2 pi epsilon naught and L with it divided by the ln of B over A. In other words, this too, the capacitance in here, has to do with the medium and the geometry, how long is this capacitor, and also the ratio of the inner and the outer radii. So as an engineer, this is what you got to do. You have to fix that so that you have that much charge enclosed. So this is still Q over C. Okay? Make sense?
Yes.
Okay. Please, I know, thank you very much, Byron. Please make sure you see the connection between the problems and the relevance of the problems we did from. As a matter of fact, I think these very same problems are actually occurring in this chapter too. So that's why they were important, the problems that we did from last time, because they help us understand what's going on. So now we have a capacitor. So from this point on, we have a device that we're going to call a capacitor. In circuits, a capacitor, they represent it like this. Two parallel wires, basically, and with conductors on this side. So usually you have a C next to it. So in some other representations, they give you, they give you something like this. It's still a capacitor, okay? They give you the value of C. So that is basically what it is, as opposed to something else, which is a variable capacitor. Anytime you see this arrow on any device, doesn't have to be just a capacitor. That means you can change the value of C on there, okay? You can play with C. Like, for example, on the old diatones, for example, that for analog devices like old radio, for example, they have actually dial in there that you turn. So what you turn, you have a capacitor that you change the area between the plates, that's all. So this is an area, this is the other area, think of the knob attached to one of the areas. As you turn it, you're turning one of them versus the other. So the area between them changes from this value to another value. As you change the area, obviously the value of C changes in this formula in here. And this one changes, okay? So that changes your your capacitor. So that is basically what you do with all the knobs. And now we have digital control of the system. So we use digital dialers and things like that. So as you change the knob, actually the numbers change and send a signal to the device to tell it to change the value accordingly. But in the old ways, it was a mechanical way of doing things. Okay? You change actually the area between the plates. And as the area changes, C changes, and a lot of things happen in the circuit. Okay? Let me play a game in here, okay? And we'll see how important that game later on. Energy. Very important game, actually, when you talk about energy. So I have a material in here, which is a conductor, sitting and minding its own business, okay? Nobody's bothering it. I have another one sitting here next to it, another conductor. Doesn't matter what the shape is. That's why I drew any kind of shape. Of course, these are 3D shapes. This is what I'm going to do. Okay, I'm going to come in here and take a charge and move it in here. So I will end up with a negative charge in here, and I leave a positive charge in here. Obviously, that's fine, isn't it? I mean, it's hard a little bit to remove a charge, an electron, for example, and bring it in here. But assume that I have a way of doing it, and I will tell you later on how we do that actually in practice. So we're going to take a charge from one end and put it somewhere else. That's fine. Then I'm not happy with that. So I'm going to come in here and take another electron. So I leave this ion positively charged. Now remember, there was a positive charge. Now it's going to be not easy to remove the next electron because there is going to be a problem, because you have to fight that. Not only that, but you have to bring it in here too. There is already a negative charge in there, and you bring another negative charge, so the repulsion now will not really be too happy. So this process becomes harder and harder with time. So the more I take charges, the more difficult it's going to become for me to do this. You guys understand? Can you imagine that at least, that this is what's going to happen? Yes?
You're just going to have to keep doing that, aren't you?
Yeah, we're going to do this, but the problem that I want you to understand is that this is going to be harder because of the fact that there is buildup of charges on one end and lack thereof from the other end. So it's not going to be easy. Yes?
Yes.
So assuming at some point, thank you, that this is my goal. I want to have a Q here. Obviously, I'm going to end up with a negative Q in here, okay? Because I'm doing it in the same time. So I will have a capacitor at the end, okay? So these two conductors will make a capacitor for me to build that goal of 100 microcoulomb or whatever charge you have in mind, okay? So that is the goal in there. So we started with 0 charge. So this is the initial. And this is the final. This is the goal. This is where we want to be, okay? Somewhere along the line in here, I'm building a capacitor now. So I know, if I know the capacitance of this capacitor is C, then I know the potential is equal to Q by definition. I'm sorry, the potential is equal to Q over C. That is how we define the potential, the capacitance. You guys understand? This is the definition of the capacitance. It's Q over C. So if I know the geometry, or if I can somehow find C, then the potential at that point is Q over C. So at some point I have a charge Q now. This is somewhere along the line. I now have Q. Not exactly the full Q, but somewhere in between. Do you guys agree? So in this case, I have removed until I have a negative Q in here. And this is my potential at this point of the process. So far, so good. You're following me. Good?
Yeah, that makes sense.
Okay, so here is the deal. I want to take the next step, which is to take a small amount of charge dq and add it in here. In other words, remove that same dq from here. So I want to transport that negative charge in here and leave this as with a dq deficiency in that negative charge and bring it in here. So that is the next goal in here, is to transport actually the negative charge, the positive charge this way if it's positive, okay? In other words, the process could work the other way around if you want to move the positive charges in the other side. It's the same thing. So I'm taking the next step now. Here is the problem. I have a potential in here. This is a higher potential. In other words, this is the electric field with which it's pointing, okay? Pointing down. Always raised from positive to negative, the electric field. And I want to build another charge dq in addition to the existing q already there, which is going to be harder. You agree, okay? And moving this dq against the field, basically, I have to move it in this direction. So it's going to cost me energy, and the energy is exactly, I'm going to call it du, which is the amount of charge times the potential in that point. Remember how much u is equal to, it's equal to qv in general. U is equal to qv. But what I'm saying now is I'm not doing a full Q, I'm just taking a small fraction of it for the next level. Because I started this process a long time ago, and since I started it, I was doing it dq at the time, actually, and moving one charge, which was from here, positive charge from here, moving it here to become more positive in here, and leaving a deficiency of the positive charges in there, which means a negative charge in there. So this is basically the process I'm doing, okay? If you think of it positive, negative charges, that's fine. Negative charges also don't like to be here too. It's the same idea. But the point being in here, I'm trying to reach this goal. This is my final, basically an ultimate goal. It's costing me energy every time we do that. And this is the energy because the potential now is building up at the rate of Q. Because I have a finite capacitance in here, C. So that means that each time I do this, it's going to cost me this much energy. So the overall energy must be, so this is how much energy it's going to cost me from beginning to end. It's going to go from 0 to Q of this dq times V. Do you guys agree?
Yes.
Yes.
So it's a matter of just doing this integration now. I know what V is. At any point, it's Q over C. So this is actually the integral. C is constant. Remember, it has to do with the geometry. As long as I don't mess around with the geometry, as long as I don't put another material in there, C is constant. So it's going to be the integral from 0 to Q of Q dq, or the integral of x dx. What is the integral of x dx? Do you guys know from your calc classes?
Wouldn't we plug in the endpoints and then take the derivative of what's inside?
No, wait, what is the integral of x dx? The entire derivative.
2x divided by 2?
Is it 2x divided by 2 or x squared divided by 2?
Oh, yeah. I'm sorry, x squared. It's early. I haven't had coffee.
Okay, that's fine. That's fine. Time change, no problem. Okay, that's fine. Does everybody agree, or this is wrong?
Yes, I agree.
So don't forget to plug in the endpoints now. The lower end is 0, the upper end is Q. So this is going to be clearly equal to 1/2 of Q squared over C, correct? So this is how much energy I'm going to do at the end of the day, yes or no?
Yes.
So if I leave the situation as is, this is how much energy I have in the system. So this device is actually a good device to store energy. And this is how much energy is stored in the device at the end of the day. Energy stored in a capacitor. Okay, good. So this device is useful, not because it only traps the electric field, which is good. Remember, the electric field is trapped in every situation in here. E was equal to 0 here too, outside, and 0 inside too. It was not 0 in here. Okay, same thing with this capacitor. E was 0 here and 0 here, and not 0 in there too. And this capacitor also did that too for us, except in the middle it's not 0. So this device traps the electric field, But actually, more important than that, it stores the energy, and this is how much energy is stored in it. So this device is a very good device because once you can store energy, you can do whatever you want to do with it. You guys understand that? Yes?
Yes.
It's actually a useful device. Stores energy. This is an important result for your homework problems and exams. Okay, you need to remember that. Otherwise, you're going to have difficulty with some of the problems that you're going to be solving. Now, let me do another thing for this problem in here. Let me take this expression and play a little with it, okay? Remember the charge. I'm going to go back to the parallel plates, okay? So I'm going to go back to two plates. I have an A in here. I have another A underneath. I'm just exaggerating the shape in here just to see what's going on in there. So I have another A in there. I have the distance between them is D. Okay, actually, this is the same distance in here everywhere. Okay, so this is like a cube, big shape and space in there. Okay, of area A and height D. Okay, so this is the height of the shape. Okay, the electric field outside is 0. The electric field inside is 0. Outside is 0. The electric field is some value in there, which is sigma over epsilon naught. And this charge Q now, or big Q, it doesn't matter which one you call, is going to be just equal to sigma times A. Okay, that's basically in a nutshell what this. Everything is in here and summarized. I have energy now stored, and the energy is 1/2 of Q squared over C. Okay, C for this geometry is equal to, first of all, let me write Q squared in here. Q squared is sigma squared A squared divided by C. C is A epsilon naught divided by D, so it's multiplying by D, okay? So this is basically where we started from. Cancel the A squared and the A. And remember, the electric field is proportional to sigma. The electric field, as a matter of fact, is equal to sigma over epsilon naught. So this sigma, I can write it as E times epsilon naught. You guys agree from this expression?
Yes.
Okay, so I'm going to express this energy now in terms of the electric field. So the energy is equal to 1/2 times sigma. Sigma is sigma squared, that is E squared epsilon squared, times the area A that is left from that. This is A squared, by the way, divided by epsilon naught, and times D. The epsilon squared and the epsilon cancel, and what in the world is A times D for this geometry? Can you guys tell me what that A times D is?
Isn't that just volume?
You guys agree with Justin? He thinks
Yes,
it's the
indeed.
volume. He thinks this is the volume of this thing. Yes? The area A times the height.
Yes, it
I know.
makes sense.
Okay, so it's the volume. So this device traps the electric field in a region of space where the energy is proportional to the volume of that space. Because that's the volume. This quantity is actually the volume of where E is trapped. And this is the E that is trapped. Okay? So this expression, I'm going to write it down now in terms of another quantity, which I'm going to define as, so this energy is in joules, by the way. Okay? So let me define the energy density, U, lowercase u, which is by definition big U divided by that volume. So the energy density, and the energy density is in joules per cubic meter, not in joules, because I'm dividing it by volume. So it's going to be joules per cubic meter. It's 1/2 of epsilon squared, cancel epsilon naught. So I'm left with an epsilon naught times E squared. This is an utmost important result. Usually when I put something in square, that means it's important. What happened when I put it in big squares? Two of them. What happens when it's like this? Is this important?
Very important.
Okay, I'm gonna say a Trump thing, okay? I'm gonna say a very, very, very important, okay? That's what Mr. Trump is. Actually, I didn't do a full Trump. I have to go like this. And then I do this. And I run out of space only, otherwise I would have continued, okay? This is of the most important expression that we're gonna see here today. Every day, this is the item of the discussion, by the way. I want you to reflect on this quantity in here. This is the energy density, not the energy, okay? Remember, the other expression for the energy is useful for our problems. So don't forget that. That's important for passing the class, basically, okay? This is also is important for down the road. It's gonna be a major, this is half the story though, not the full story for telecommunications and how your antenna works, okay? And we still have that coming down the road. So it's an energy density. This looks like an X, it's actually a U, lowercase u. Okay, so it's a joule per cubic meter. It's proportional to the square of the electric field. So if the electric field is changing from positive to negative, it doesn't matter. When you square, it's going to be positive. Just like a kinetic energy. Your kinetic energy, your car, for example, can be going in one direction, another car can go in another direction. So the total momentum could potentially be zero because if they're moving with the same velocity and have the same mass. So the momenta in this case add up to zero, they cancel. So the velocities, they cancel because they have in different directions. But the kinetic energy doesn't. The kinetic energy is proportional to the square of the velocity. So in this case, this car has a kinetic energy, this car has a kinetic energy, and when they cross each other or they collide, they have tremendous amount of kinetic energy that is in this case exchanged in the process. Now, that is because it's proportional to the square of the quantities. So the initial kinetic energy is huge, regardless of which way you're moving. In a random motion, for example, for physics C, I know some of you are, we'll discuss that in chapter 18, where there is a random motion, and that random motion leads to the concept of temperature. So that is actually related to the kinetic energy. This quantity plays a major role. This square in here plays a major role in physics, not just in here. Even the foundation of quantum mechanics on how to understand quantum mechanics, telecommunications, also these chapters, I mean, that are coming down, there will be another half. So this is not the full story. This is half the side only, half the story. The other half, you're going to remember this day. Today is March 16th. The next time we see this expression similar to it, I'll tell you the other half. So this is half the story, okay? And how this thing is working. Every day we met in here in this class, Physics 4B, from day one. If you guys remember, go back through your notes, go back through the pages of the book, go back through anything. Epsilon naught lived downstairs. It was always 1 over epsilon naught, all the time. Today, for the first time, it moved to the numerator. It's upstairs, okay? Remember, epsilon naught itself is a tiny quantity. So this energy density in here is going to be small, but it's a big, important result in here. Yes? Are you guys excited about this, or am I the only one?
Oh, it's very cool to see how this is all coming together. The capacitance, I'd never known it kind of worked like this. I've seen a capacitor up close and I've dissected it before because I'm very into electronics, but yeah, to think that this would be all coming together like this is really cool.
Okay, so here is the point, Byron, that this device stores energy. When you have a volume, and inside that volume, we have electric fields pointing every which way. This is now removed from the capacitors. This has nothing to do with the capacitors, by the way. The geometry of the capacitors is gone in here. Remember, that volume had A and D in it. We removed them. So this is true everywhere. Even in space, this space, for example, before my hand and here, or near my eye, and how my eye, the receptacles in them, and how those things move up and down, they're in response to the electric field. And they're taking that energy that is hitting them and basically making them move up and down. So converting that energy, this energy. So if you have a region of space, because now we're not talking about that because we want to, so if you have a region of space, the electric field is pointing every which way, so it's a random directions, but each one of them brings an E squared. Namely, it's like the velocity squared, velocity squared, velocity squared. So now you have effectively an amount of energy. So this expresses a bundle of energy once you have an electric field. So this room that you're sitting in right now has tremendous amount of energy, and it's all expressed through this form. Okay, so I hope that you guys ponder about this expression, think about it, think in terms of mathematically the fact that it's an E squared, what it means for the random motion of the electric field pointing every which way, but then at the end, when you square them, you're going to end up with something that is always positive. So regardless of which way they point, this epsilon naught, the fact that it has now, for the first time in this class, has changed location. It used to live downstairs, and all of a sudden have found itself upstairs. Okay, used to live in the first floor. Now it's actually living in the second floor and making a lot of noise upstairs. Okay, and this factor of 1/2 were just really for this coefficient of squared. Came from that, remember that integral of x squared. That's where the 1/2 came in. So the capacitance is a good device to store energy. This is the energy in the capacitor. Is that Q squared over 2C? There is another way of writing that expression. Remember, the potential, Q is equal to CV. Another way of writing this expression is actually U is equal to 1/2 of CV squared. The C is written in the numerator, and the V now is written in here. So that's another way of writing this expression. And sometimes you use one or the other depending on the problem. Okay, both of them are the same. Okay, this relies on the definition of how Q and C are related to one another. So far, so good? Yes?
Yes.
Yeah.
Okay, I know that, especially if you have not seen this stuff, it may be overwhelming a little, so please don't hesitate to go back into the notes, come back to this video, see this discussions, and go through it, go through the problems in the book, the examples. We're not going to do plenty from this chapter. Okay, Thursday. Here is another device that we need for the next part. A battery is usually represented this way. So this is the cathode of the battery. This is the negative plate. Every battery that you have, and I used to have plenty of batteries, and now here is battery. Okay, this is a 1.5 volt battery. It has a plus on one side. I don't know if you can see it or not. Oh, did I turn it the wrong way? And it should have a negative to the other side somewhere. It's not written, it's implicit. Okay, batteries usually have a plus and then a negative from them. So this is the cathode, this is the anode of the battery. This is a plus. So this is represented by a big leg. This is represented by a short leg. Another device that we're going to use in this class extensively is the switch. The switch is either on and off. This is a regular switch. There is at some point we're going to be using an AB switch, which can have 3 positions. So at this point, we're going to just concentrate on a switch that is on and off, basically the switch of your home. Okay, turn on and off the power. Okay, that is basically how we're going to do. So in this thing in here, this is a switch. So what is the role of the battery? The role of the battery is to maintain the voltage difference between its nodes. If you go to this store, for example, this is a 1.5 volt battery. If you connect it to anything, and that doesn't matter which, charges start to flow. Okay, starts to flow. Actually, electrons move from the negative to the positive, but we say that positive charges are moving from positive to negative. It's the same thing, amounts to the same thing. So these charges, when they move, they come in here and they cancel the negative charges. The battery doesn't like that because that will cause the voltage to drop. So the charges will drag them against their wish. They want to be here. If you bring a positive charge in here, a little positive charge in here, it wants to be in this area because then it cancels whatever negative charge is in there. And that's equilibrium. That's what you wanted to see. And then when it departs from this region, so it leaves basically some of these charges to be distributed in here. And now you have cancellation on both sides. The voltage drops. The battery doesn't like that. It's going to take that positive charge that came from here and move it to the opposite charge, where it doesn't like to be, because this is a place where there is a crowded already places with positive charges. And the battery will do it against the wish of this place because it was already negatively charged region, and it's going to make them more negative. But the battery has a secret. It uses chemical energy to do that. Okay, and as long as it has that secret, the battery is good and you can work with it. If it runs out of energy, that is the time when you go and basically pay another $4 for another set of batteries. Okay, so this is the battery. This stuff that I was describing about the battery is called the electromotive force. Electromotive force, and sometimes force, sometimes is referred to EMF. Okay. So for right now, it's a voltage. It's 1.5 volt for this specific battery, okay? That's all there is to it. So 12 volt battery, for example, for your car, is 12 volt battery. It's EMF. So if the voltage drops, kicks the generator, pushes more charges, and now it's back to business. It uses different process, but it still maintains its voltage there. When you time to crank and turn on the car, it sends that current for the car to start, and then it starts, generates back itself, and it stays at all. As long as it's good. Then when it runs out of chemical energy, again, you go and pay $150 or $170 for batteries nowadays. Okay, so this is what the battery does. So this is what I'm going to do. I'm going to take a capacitor. I'm going to call it C1. Okay. And then I have another capacitor, which I'm going to call it C2. I'm going to connect them together to a battery of a given voltage. So this is the plus, this is the minus. For convenience, I'm going to throw in a switch in here to help me with my circuit, okay? Usually you need a switch, but for this purpose, you really don't care for it. Let's close the circuit in here. Let's make the switch on. So the switch is basically closed right now. So it's all just a wire in here. So here is the deal. So what is the switch in here? So this is the switch, by the way, I forgot to mention. Yeah, it's a switch, S. Okay, so we have a battery. It has a certain voltage across its ends, and it wants to maintain them no matter what. So this side is connected to the positive. So now charges flow and pile up in here. Okay, so this is positive Q. Obviously, there is a deficiency of positive charges. So this one will get rid of the negative charges enough in here on this side to maintain the voltage across its ends the same. So there is a negative Q in here. It has to be the same value. Understood so far? Yes?
Yes.
So they are connected. So this happens. Now, this is a capacitor. On one end, it's a negative Q. From the other side, it must have a positive Q because this is a capacitor. The only way for the capacitor to work is when the two ends are balanced. So now you have a positive Q in here. This was neutral wire. It did not have any charges in it. So you cannot have a positive Q sitting by itself in here. You must have a negative Q, the same Q in there too. So this is the distribution of basically how this thing looked like. Okay. So starting from the negative to the positive, I'm going to start labeling. I'm going to label this one starting point. Jump over the capacitor, call it the second point. Jump over the second capacitor and call it the third point. Okay. What I'm interested in is the difference in height in potential between the third point and the initial point. It's like the floors, for example. You live on the first floor, somebody else on the second floor, and somebody else is on the third floor. How many floors are you between the first and the third? Is really the sum of this. You go from the first floor to the second floor and from the second floor to the third floor. Identical. The voltage and the height are similar in this situation. So what you say in this case, to go in voltage, you go from first to second, and you go from second to third. It's the same thing as that voltage. Make sense? Make sense? Good?
Yeah, it makes sense. Yeah.
Okay, so actually this voltage is the same voltage across the battery. So this voltage is that of the battery. The battery wants that voltage to stay the same because these are wires. They have no effect whatsoever on the voltage. So a wire has no, you don't change voltage on a wire like this one in here, okay? So this has no voltage whatsoever difference between them. So wires have no voltage dropping or adding or anything like that. It matters only when you cross devices. And here there was a problem if you didn't balance the charges. Okay. Now here is the problem. The voltage across this one is capacitor of a capacitance C2 and it has a charge Q. So the voltage in here on capacitors 2 is Q over C2. The voltage across this one in here is V1 and it's simply equal to the charging on it, which is Q over C1. So I know the voltages in here. So how much voltage is from here to here? That is the total voltage. So the voltage in this case is going to simply be equal to the sum of the two voltages. So the voltage is going to be V1 plus V2. It's like how many floors are between the third and the second? It's 2 floors. It's the floor between 1 and 2 and the 2 and 3. Okay, same thing. So that is exactly what this thing is saying. If I do it this way, this configuration, by the way, is called in series. So I have 2 capacitors in series. The charges are the same. So when somebody tells you something in series, the charges are the same. End of the story. It means the same thing. So the word series and this one are the same meaning, okay? Now, I know what V1 is. It's Q over C1. It's the charge of the capacitor in C1. And I know what V2 is. It's the charge Q, the same charge Q, by the way, because it's in series, divided by C2. Okay, from the vantage point of the battery now, this is what the battery is looking at. The battery looks like this. It sees 0.1 and it sees 0.3. Oblivious to the fact that there are devices in between them, it sees a big charge Q in here and a negative charge Q in here, end of the story. It sees this thing in here, a big Q and a negative Q, end of the story. It sees a big capacitor, actually, of capacitance C equivalent. So the battery in here looks like this. For it, this is nothing but a Q divided by some C. Okay? So this is the equivalent capacitance. C equivalent is the equivalent capacitance of the two. As if, this is not real, this is as if, okay? There is only one capacitor. In practice, there are 2 of them. Really, there are 2 of them. But in here, the battery sees as if it's only one of them. And the capacitance for that is given by that expression. Obviously, Q cancels from both sides. So this Q and that Q and that Q cancels. And the equivalent capacitance in this case is going to be just given by this expression. So 1 over Q, 1 over Q. 1 over C equivalent is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth, okay? So in other words, C equivalent is going to be 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth. I mean, I did 2 only, but you can think that you can have more than 2. Don't forget that you have to raise this to the negative 1/2, okay? You have to invert the expression after you find it. So this is the equivalent capacitance. So let's think of this problem now and see what's going on. Let's take an example, okay? Let me take, for example, this capacitance, 2 microfarads. This capacitance, 4 microfarads. This capacitance, 6 microfarads. Why not, okay? And what is the C equivalent in here? See, I don't like 6. It's going to make it dealing with a fraction of 3. I don't like that. Let's make it 8, okay? Much easier, much nicer. So the C equivalent now is going to be clearly equal to, this is what probably Marcella was referring to in the beginning. So pay attention to this thing, okay? It's 1 over 2 plus 1 over 4 plus 1 over 8 to the negative 1 in microfarads. So what she was saying in here is don't put 10 to the negative 6. Don't put 10 to the negative 6. Don't put 1 over 10, 2, 10 to, just leave it at the end. Just deal with these numbers only. Okay? Do you guys understand? In doing this problem, this is actually a good strategy, good technique. Not to bother with the power immediately. Leave it toward the end. Leave everything on the same unit and move around. Now it's easy to do 1 over 2 plus 1 over 4 plus 1 over 8 because the common denominator is clearly equal to 8. So this is going to be 4 This is going to be 2, and this is going to be 1. So it's clearly 7/8. But don't forget, I'm inverting that. I have a power to the negative 1 in here. So the answer of C equivalent is going to be 8/7 microfarads. You guys understand in here how to find this thing? So this is what Marcella was talking about. Is that correct or not, Marcella?
No, yeah, they basically converted it at the very end. So like if they had 10 to the negative 20, they converted it at the very end to be
Yeah,
like
so,
the whole number.
Yeah, so it's easier to deal with whole numbers this way. Leave the micro, make sure everything is in micro though. If one of them is in pico, convert everybody to pico. If something is in nano, convert everything to nano, and then the answer is going to be in nano. But then the other numbers have to change accordingly. That's the only difficulty that you have. But most of the time, the capacitance are in the same unit, okay? If they're micro, leave them all in micro. So in this case, deal just with this fraction, which is easy to do, and then at the end, just invert it. Don't forget the negative 1 in here, and that is going to be the answer. Here's the deal. If you look at my example, this is 2 microfarads, this is 4 microfarads, this is 8 microfarads. When they are in series, like this one, the equivalent is less than the smallest of them. So this is general actually consensus. So capacitance in series, the equivalent capacitor in series, the equivalent capacitance in series is smaller than the smallest. So this is one way to check your work. If you're doing a problem and you find more than 2, like 2.5 or 7 or 8 or any number more than 2, you know there is something wrong. As a matter of fact, if you find 2 is wrong, it has to be less than. It cannot be less than or equal to. Okay? So this is basically in a nutshell what's going on with the capacitors when you're doing them in series. So in here, it's clearly 8/7 is less than 2, less than any of the others. If it's less than 2, it's less than everybody else. So when you're doing stuff in series, the equivalent capacitance is less than the smallest of them all, okay? Here is another configuration that we're going to do. It's similar to this one, except now I have a different arrangement. It's called in parallel. So when I have capacitance now, this is C1, and this is C2. And now I connect this end to a battery. Of course, don't forget the switch to make things work. Obviously, this is not going to work in practice if you do it, because the current will be so high that it's going to short circuit the battery. It's not good. Don't do it straight, okay? So there is a switch in here, okay? Now, this is positive, this is negative, so this is the voltage across. So this is the voltage across the entire battery, okay? Now, here is the problem. When this side drains charges, some of it will come in here, negative Q2, and some of it will come in here, negative Q1. On this side, you have a positive Q1 and a positive Q2. Because of this junction, the charge is split some ways this way and some ways this way. Is it halfway? It depends on C1 and C2, how big they are. If they're the same quantity, it's going to be the same quantity. If C1 is equal to C2, they are going to be split in half. But if they're different, it's going to go on one side than the other. So here is the deal. How much charge did we take from this end then? You guys see that we took the sum of the two, because it must be we have taken Q1 plus Q2 in here to make it to this point where they split, so that the charge is the same in here and there. So Q must be equal to Q1 plus equal to Q2. The reason why that is because this is conservation of charge. Okay, make sense? Which is actually they combine again back in here, and they're in here the same thing as negative Q1 plus Q2, negative Q1 and negative Q2. So the charge is conserved in here. Makes sense or not?
Yeah, it does.
Okay, very good. Now I'm going to go from this potential in here. I want to find V now across the battery. So this is one way for me to go across the battery. So this is one route. Another route will be this way, and both of them must be the same battery of the voltage of the battery, because this point is actually this end of the battery and this point is the other end of the battery. So because of the fact that it's split in here, it doesn't matter. This point and this point are the same. So the voltage across the battery, V, must be on one side, this voltage, which is Q1 over C1. And in the same time, must be Q2 over C2. So that is how the charges actually are split, to maintain the voltage across the battery the same. Remember, there must be the same voltage across the battery. That is what the battery does. So this is a requirement for this condition, okay, for how Q1 and Q2 are related. As a matter of fact, I can write Q1 in here to be C1 times V and Q2 to be C2 times V, simply, okay? So again, the Q overall that is drained from the battery is just the sum of these two Qs, remember, Q1 plus Q2, which is C1V plus C2V, which is equal to, again, C1 plus C2 times V. Again, from the vantage point of this capacitance, this is what the capacitor sees. I mean, what the battery sees. So the battery sees this. From one end, you took Q from it. It doesn't matter how you split it in there, between Q1 and Q2. And from the other end, you took the same Q from it. So this is a negative Q. This is a positive Q you took in here. So there is a positive Q in here somewhere. And there is a negative Q on this side too, okay? So the battery sees the same thing, sees a C equivalent in here, okay? In such a way that the voltage across it in here, the voltage across the ends of the battery, which is still V, by the way, V is equal to the Q that you took divided by the C equivalent. In other words, Q is still C equivalent times V. If you compare these two expressions to one another, you find that the C equivalent is just the sum of the C's. So the C equivalent in this case would be simply equal to C1 plus C2. If you brought a third capacitor to the equation, it's going to be plus C3, and so on and so forth, as long as you have a parallel capacitors or capacitors in parallel. Okay, to go back into my initial example that I gave, I take 3 capacitors now and I put them all in parallel to one another. So again, I have my 2 microfarads. I have my 4 microfarads. And I have my 8 microfarads. I put them end to end. Like this, connect them like that, okay? At this point, it doesn't matter if I put them across a battery or not, because all I'm looking for is just a C equivalent. Obviously, the C equivalent in here is going to be 2 plus 4 plus 8, which is 14 microfarads. If you compare the 14 microfarads to any of these numbers, it's bigger than the biggest of them all, which is the opposite of how capacitors work in series. So capacitors in equivalent capacitance in parallel is larger than the largest. Again, this is how you check your work. If you look at the configuration that involves one or the other, and then all of a sudden you see the capacitance and you find it less somehow than one of them, than the biggest one, because if it's less than somewhere else, it's going to be less than more than one, then you know that you did something wrong, that there is an issue in there. So if they were in series, it's going to be smaller than the smallest of them all. If it's going to be in parallel, that's going to be larger than the largest of them all. So that is basically how you do circuits with capacitors, okay? Now, these two results are of importance also, both of them for your homework and your problems. And as a matter of fact, we have several problems from this chapter that we're going to tackle. Let me tell you what the problems are. I know we still have a few minutes and we're going to dismiss, but the point is I need to get into the problems. Okay, we're going to do problem 1, just to play around with how to find the capacitance for a simple geometry, okay? Because it's important. As engineers, you really need to do that. We had a lab where we used to do it, actually you build your own capacitor. And that is an important. And the lab on Thursday is going to be dealing with that. So we're going to be dealing with that expression. So it's important. Problem 51, problem 53, and problem 57, and problem 59. So those are the problems from the 15th edition, of course. If you don't have the 15th edition, you should have access to the e-text, in which case you should have access to these problems. Again, problem 1, 51, 53, 57, and 59. I think one of them probably has to be changed somehow. I may have to change or alter some of these problems if I don't have time to see how things go, because I think problem 56 looks promising, honestly. And problem, yeah, 56 looks good, and problem 55 and 54 look good. So at this point, we need problems with the energy, actually. That's why I want to have problems with the energy, because in a case of an exam or somewhere else, you will deal with the energy too, okay? You will be dealing with the energy. Okay, chapter 25, which is the next chapter next week, is going to deal with the resistors and more in circuits, okay? In chapter 26, we'll really delve into circuits and get stuff into circuits, okay? You see how we moved away from F equals to MA? Now we're getting into circuits and electronics and stuff like that, electricity. This is how things evolved on their own, okay? And now we're getting stuff from this ones in here. I'm hoping, and I think we are going to get everything ready before the spring break, in which case you're going to go and get prepared for your exam, which is going to be on campus. So the discussion point today, if you guys remember it, has to do with that big and huge fuss that I made about the expression involving the energy density. So I want you to really ponder about that expression. I want you to also think about what Marcella had said in terms of how to tackle these problems, because I think it's an important point, and that do not be tempted to start to putting your powers until the end. Those are the two items really, because she brought up an excellent point, and I really want everybody to be on board with it on how to do problems without having to waste a lot of time on this unit stuff, because you get lost in numbers somewhere and then it's futile at the end. Becomes messy. Make sense?
Yes, Professor.
Yes, Professor.
Very good. So I'll see you guys Thursday, same time for lecture, and the lab is going to be in the evening on Thursday. So let me stop this thing in here. Stop sharing, that is. And if you guys don't have any questions, I'm going to stop the recording, and I will see you guys then.
Sounds good. Thank you.
Alrighty. See you on Thursday.
Thank you, Professor.
Bye.